I'll start with structured perceptron and margin methods. So I think I want to give a little bit more of an algorithmic description and like closer to actual implementation that was in the book, in the reading. I think the reading was kind of abstract and mathematical, so this will probably get you a little bit closer to actually implementing the things. And also, of course, I'll expand on the ideas like I do always. So. Okay, so I'm going to talk about the structured perceptron and margin methods. And as we've talked about before, we talked about our different types of prediction, binary classification, multi-class classification, structured prediction. Most of the time when solving any of these models, any of these things up until this point, we have used probabilistic objectives, objectives that calculate a probability distribution or something like this. The ones that I'm going to talk about this time aren't necessarily probabilistic and can be applied to any of these types of prediction. But because this is the neural nets for natural language processing class, I'm going to mainly focus on structured prediction methods. So yeah, I talked about the many varieties of structured prediction as well before. So we've covered these ones already. And I'm going to talk about sequence level likelihood and structured perceptron and structured large margin today. So as a reminder, globally normalized models versus locally normalized models. So locally normalized models, each decision made by the model has a probability that adds to 1. So at each decision we renormalize the probability. We calculate a softmax, in other words, and use the probability there. In a globally normalized model, we have a single score here. And then we normalize over the whole, output. And I've talked about these models before in the previous classes, but this is going to be important because of the contrast that it draws to the other models. So first, globally normalized likelihood. So we talked about the difficulties training globally normalized models, which was calculating the partition function here. Because we can almost always calculate the score of two, an input and an output. We define it in a way that we can calculate the score of the input and the output, but then we can't sum over all possible inputs and outputs. And there's kind of two options for calculating the partition function here. The first one that we talked about was use some sort of structured model to allow enumeration via dynamic programs. So when I say structured model, I mean, it takes in the structure, does some sort of dynamic programming over the decomposition structure, local independence assumptions. It calculates the output, and we had like the linear chain CRF and CFG as examples of this. And another option is to estimate the partition function through subsampling the hypothesis space. So an example of what we can do here. So with respect to sampling, the slide names are a little bit confusing. So when I'm talking about subsampling, I'm talking about not enumerating this whole sum, but rather enumerating part of the sum. A subset of all of the possible sentences. And there are two methods for doing this, this subsampling. And the first one I'm going to call sampling, probabilistic sampling. And basically what we do is we sample k outputs, like let's say k sentences, if we're doing a sequence-to-sequence model, according to the probability distribution. And then we use this to approximate our partition function. So instead of summing over all of the things in the vocabulary, we sample over k samples. We sum over k samples. So there's an advantage of this. So this advantage basically will this gives us an unbiased estimator that we, as k gets larger, this will approach the true distribution. The problem with this is high variance. So like, for example, let's say we sampled by chance, a few things that were really low probability, or like 5 things that were really low probability, then suddenly all of them, would be low probability. It wouldn't be a good estimate of the true hypotheses that our model should be competing against, and it's not, an effective way of training the model. Another option that you can use here is to use beam search. So basically, beam search searches for the k-best hypotheses and uses the k-best hypotheses to calculate this partition function. And the good thing about this is basically that these k-best hypotheses will likely be high-scoring hypotheses, right? So they're likely to be the ones that our true hypothesis should actually be competing against. But the problem is that this is a biased estimator also, and it may result in systematic differences from the true distribution. It's also lower variance, but the good side is it's lower variance. We're more likely to get high probability outputs. So this is a little bit of background. So this kind of moves from likelihood to globally normalized likelihood. But I'm going to be talking about unnormalized models, mostly for this time. And what do I mean by an unnormalized model? So a normalized model is a model where the output distribution is a good probability distribution. So all of the probability of all the hypotheses are between 0 and 1 and sum to 1. That's the definition of a probability distribution. But at inference time, often we just want the best hypothesis. We don't actually care about probability. There are some counterexamples to this, like where do we what is an example of an application where we really do care about the probability of the output? Anybody? Yeah. Ranking more than one option. That's a good idea, but no, because you don't actually need a probability to rank. You just need a score to rank. So if you wanted to rank the number 1, number 2, number 3, and number 4, even if the probability was not normalized, you could still use the score. Okay, sure. If you wanted the top 1% of the results, then yeah, that would be an example. So then you would enumerate all of the top ones until you got down to a total of 1% of the probability. That wouldn't actually give you the top 1% of the results, though. I guess it would give you the top 1% of the probability mass. But yeah, I see what you mean. Yeah.
If you want to give a confidence score with each prediction?
If you want to give a confidence score with each prediction. So yes, this would be one example. You want to say, I think this is the best answer, and I'm 20% certain of my assessment. Oh, as kind of an aside, how many people have heard of the concept of calibration? I'm always surprised that this is not something they teach in every single machine learning class, actually, but this is a really important concept. So I have to teach it in neural networks for NLP for some reason, so I will. But calibration, the basic idea of calibration is, oh, there's an excellent blog post about this, actually, at a political blog called 538. And basically, the idea is they want to make predictions of who's going to win a basketball game or who's going to win a presidential election. And basically, I don't remember exactly how they calculated the error bars, but what they did was they took all of the predictions where they have 0%, where their model predicted with 0% probability that the event would occur, about 5% probability that the event would occur, 10, 15, 20, 25. And then post hoc, they checked how often the event actually occurred. So if you have a perfectly calibrated model, what this means is if you say there's a 30% chance this will happen, it actually happens with 30% chance. So for sports, they're actually pretty good at predicting their probabilities. Note that calibration is different than predictive performance. So, like, let's say I wanted to create a predictive model of a coin flip. A predictive model of a coin flip would be a really bad predictor. It would get it wrong half the time because it's a random event that, unless you have a weighted coin, it's a random event. But I could say I have 50% confidence that this will be heads, and you would have 50% chance of it actually being heads. So that would be a well-calibrated model that has poor predictive performance. So neural nets tend to be good predictive models, but very poorly calibrated. So basically, what this graph looks like most of the time is in neural models, especially kind of overfitting neural models, is like, let's see. So the x-axis is how much, the y-axis is how much it actually happened. The x-axis is how much the model predicted it would happen. And so basically, the model, something like this. So the model is like super confident that it's going to happen all the time, but then it's wrong a lot of the time. So it says, I'm 99% sure that this will actually happen, but then it actually happens about 50% of the time or something like that. So neural models tend to really strongly overfit and be way overconfident. There are ways to fix calibration. A very easy way to do it is to do it post hoc, which is basically to create the opposite graph where you calculate kind of the score range in which you have 100% correctness, 90% correctness, 80% correctness, 70% correctness, and like essentially fit a nonlinear regressor to try to predict the actual confidence given the output that your system gave. And then, at least if you have a monotonically increasing score, chance of it actually being correct, based on the output confidence, you can push the curve up to the actual appropriate confidence values. So this is calibration. This is like, if you have a probabilistic model, how good of a probabilistic model is it in the first place? So, I suggest you read this blog post if you like politics or sports or calibration. Cool. Okay. Some other examples of where you might want probabilities is if you are feeding the predictions into a different downstream model. So let's say you had a downstream model that took in let's say you had a downstream translation model that took 5 upstream speech recognition results or something like that, a speech to text translation model. If that was the case, you would probably want your downstream translation model to know how confident the speech recognition model was in its results, and a well-calibrated probability would be another way to do that. So there's a bunch of reasons why you might want a probability, but if you just want predictions, actually you don't care about probability. You just care about how good the prediction is, right? Okay. So at inference time, we often just want the best hypothesis. So what we are doing is we're taking our probability and we're taking the argmax of that probability, right? But if we look at our globally normalized model, or locally normalized model for that matter, because we're formulating it like this, the thing with maximum probability is also just the thing with maximum score, right? So we don't actually need to do normalization. We could just find the thing with the maximal score. So if we don't need a probability, that opens up our possibilities to lots of other things. So one example of a structured training algorithm is the Structured Perceptron Algorithm. I think in the reading it was called like the Global Perceptron, or I forget exactly what it was called. It's normally called the Structured Perceptron Algorithm. And it's an extremely simple way of training non-probabilistic global models. And basically what you do is you find the one best output according to your current model. And if its score is better than the correct answer, adjust the parameters to fix this. So this is the algorithm. This is your beam search or greedy search or whatever way you can find the thing with the best score. And if the score of the thing that you found is better than the actual best score, then you take the gradient with respect to the difference between these two. scores. So what this is doing basically is it's taking the score of the true value and improving it, and taking the score of the false value and decreasing it. So is that okay? So one thing that's nice about this is you can do this in a model where you can do argmax search easily, but maybe not necessarily, or do approximate argmax search easily, but not easily, sample a lot of outputs or something like that. Yeah.
Why not always increasing kind of reinforcement the probability that, or why not having always the term that maximizes s of y given x, since y is always, we know it's correct.
So why not always have a term of s of y given x, or increase the gradient of s of y given x? So actually, I'm going to have that on the next slide. So we'll get there. So if you think about the structured perceptron loss, like what is the loss function in structured perceptron? You don't actually need an algorithm. You can just calculate it like this. So what you do is you take the max of 0 and this. In reality, if you had a perfect search algorithm, you wouldn't even need this max of 0. And the reason why is because this is this is the highest scoring thing. This is the thing with the maximum score according to your model. And this is something else, or this is at least, this is the true reference. So if the true reference got the highest score of any of your possibilities, y hat and y would actually be the same thing. So y hat and y would be the same thing, so they would just cancel out and become 0 anyway. And any other value, this would be bigger than this, so it'd be greater than 0. So you actually don't even need the max here if you're just using the standard structured perceptron algorithm. Yeah?
You had an approximate search for the y hat.
Mm-hmm.
Is there any benefit provided by having the max function? Let's say if you didn't kind of find out what the value for the actual goal reference.
So if you have an approximate search for y hat, is there value in having the max function? Probably. I actually don't have a really strong intuition about it because I actually don't see a lot of trouble penalizing the thing that you found anyway, if that's your search algorithm. So you might not even need the max in this case. I have an ulterior motive for the max, which is it does become important in the next few slides. So the resulting gradient looks like the perceptron algorithm. So basically it looks like this. This is a normal loss function, so you could also use it in a neural net if you wanted to. You definitely could. So I'm going to get back to the question here. And the question here was basically, why don't we always increase y? And the answer is actually, if you reinterpret it a different way, we actually are always increasing y. Because in the case where we have exact search, then y hat and y will be equal every single time this otherwise happens. So in that case, we would increase this, but we would decrease the score of the same hypothesis by the same amount, and they would just cancel out. So we actually are increasing the score of y every single time.
But we don't have exact search.
But we don't have exact search. So this algorithm only has theoretical guarantees in the case of exact search, and when it's approximate, we don't have such guarantees, but it kind of works anyway, so yeah. Any other questions?
The y hat which you mentioned is the best probable answer given by our search algorithm, or is that the
By our current model, yeah. I have not equals to y here, but you can actually ignore that not equals to y for the structured perceptron algorithm. You can't ignore it for the next algorithm, which I'm going to talk about, which is the structured hinge loss. But yeah, it is the argmax according to the current model.
And so that argmax is being found by our particular model itself, or by some inference algorithm, or is that the global aspect?
It's the inference algorithm is finding it. Yeah.
So there might, so as a follow-up, so there might be a possibility that the current y hat with the inference algorithm chooses not be the best one.
May not be the highest scoring one, and yeah, that's very likely if you're using a complicated model. However, as I said just a little bit before, I can reiterate this, that might not necessarily be a bad thing, because that is the thing that your inference algorithm is finding, and that's what your model is going to output at test time, right? So even if it's not the highest scoring one, you might still want to penalize it anyway, so your model is less likely to find it. So, yeah.
So coming back to the question on why do we also decrease or have this negative term, is that also not because we want to learn negative weights for certain features? If you talk of classical perceptron, and if we don't have those things, then we won't be able to do that essentially. So we need some negative weights.
So we want to learn negative weights for certain features. Yeah, I actually think the question was not why don't we decrease the score. I think, yeah. But anyway, yeah, we do decrease the score of the found one because we want to decrease the score of negative features. So that is very true. Okay. So we have this. So contrasting perceptron in like a globally normalized probabilistic model. In the globally normalized probabilistic model, this is what our loss function looks like. So we have our log E of score divided by the partition function. So it looks like this. We could also have something that's a little bit like the global structured perceptron. So basically, we find all of the competing things, and we take this value as well. So in this case, we really do need this max function because we would only be decreasing them if they were worse, if they got a higher score than our actual true output. So this would basically be saying, I'm going to increase the score of the correct hypothesis and decrease the score of all the other hypotheses. However, this has the same problem, right? We can't enumerate the sum, so we can't actually calculate this in practice. Okay? So, yeah. So one good thing about these structured losses is, like, very intuitively, we're downweighting the thing that we actually found and our model is going to output. According to our current inference algorithm. And that's a good thing, right? Like if our model found something that isn't a good hypothesis, we will want to penalize the thing that it would have incorrectly gotten. It's aware of our search algorithm in a way, because it's downweighting the thing that the search algorithm actually found. However, it has a disadvantage, and the big disadvantage is that because neural networks have lots of parameters and a big output space, training is hard. So we have a trade-off between these two algorithms. So selecting just one negative example, and the big problem is selecting just one negative example is inefficient. So if we think about our locally normalized, regular sequence-to-sequence model, for example, the locally normalized model was actually penalizing every single negative example within the space of the vocabulary at each time step. So it is, literally penalizing every example. It has problems, like I talked about, exposure bias and teacher forcing. It's actually not connected to the thing your model is going to output, but it does have that going for it. The common thing to do here is basically to pre-train with teacher forcing for a certain amount of time, and then switch over to a structured training algorithm at some point during the training process. Maybe it's when your model has converged. Maybe if you wait until your model has converged, it's too late because it's already overfit to the training set, and you would want to wait. You would want to stop training a bit before the model is fully converged on the training set. So, any questions here? The obvious question is, when do you choose? And I think there's no really clear answer to that. It's probably an empirical problem. Okay, so the next thing I'm going to talk about is hinge loss and cost-sensitive training. So if you've taken a basic machine learning class, you probably have seen something that looks a little bit like this at some point. Unless, how many people know support vector machines? Most people, okay, good. I'm always a little bit nervous with the new like deep learning wave that people have about what concepts are still around and what concepts are obsolete. So support vector machines is one that's still around. But basically, support vector machines, the idea behind them is you want to find the boundary between, or a decision boundary that has the maximal margin. So what is the largest amount between the decision boundary and your examples? So in this case, the margin for the dashed line is pretty big because you have a big difference between the margin, the boundary, and all of the examples, and the dotted line is small. So this has a small margin. So we would prefer the dashed line here. But notably, both of them have zero perceptron loss. They both are perfectly good decision boundaries. So we can add a margin with a hinge loss. So this is different than kind of the standard training algorithm for support vector machines. Support vector machines do a lot more complicated things, which is calculating kernels and doing optimization of the margin directly using batch training. But there's a really easy way to incorporate this in neural networks. And basically what we do is we take our perceptron loss, which looked a little bit like this. So we have the difference in score between the highest scoring hypothesis and the hypothesis that we actually found. And we move it a little bit like this. So now, if the highest scoring hypothesis is, for the perceptron loss, if the highest scoring hypothesis is better than the true hypothesis, we get a penalty. Now we get a penalty even if the highest scoring hypothesis is better, even if the true hypothesis is better, but it's not better by enough. So in this case, we're saying it has to be better by 1. So if it's not, the difference between them is less than, or is more than -1, then we still get a loss. So what that looks like is we add a margin, we add the score here, and we subtract the score of the true one. So if this margin is 1, it would look a little bit like that. Okay. So the nice thing is, anywhere you have a softmax, you can also use a hinge loss if you don't care about probabilities. So let's say we have a part of speech tagger. And normally we would have our softmax over all of these things. You can just as easily use a hinge loss. And sometimes this is better, sometimes this is worse. Sometimes it's actually quite a bit better at optimizing things well. And there's actually a really nice example that kind of intuitively makes a lot of sense to me when you would want a hinge loss and not for example, a probabilistic loss. So let's say we have a binary classification problem. Is that enough? Okay. Let's say we have a binary classification problem that looks a little bit like this. Where would hinge loss draw its boundary? This one's kind of easy, so I'll give it to you for free. It would draw, maybe something like a little bit like this, right? That's the maximal margin. So what about your logistic regression classifier? Any ideas? Let's say your sigmoid looks about like this. If we drew it on this decision boundary. Would it be down to the left or out to the right? Yeah, it'd be down to the left. Something like this. And the reason why is because there's a ton of positive examples. There's only a few negative examples, and it really doesn't want to get a lot of loss on the positive examples, so it moves it away from the positive examples, even at the risk of sacrificing the negative examples. So if you run a logistic regression classifier, you have no guarantee that you would, you have no guarantee that you would find a balanced place. In reality, another thing that a neural network or whatever, an unrestricted logistic regression classifier can do is make the scale of your values really large, right? So it will make the scale of your values like super big. And so what it will do is it will take your sigmoid and make it look like that. Basically, it will take the sigmoid and make it not a smooth sigmoid, but make it really, really peaky, and then you can draw the same line. You can get 100% classification accuracy here. But no, you have a super poorly calibrated classifier, right? You have a classifier that thinks it's super confident all the time, and then you get a slightly different distribution. You get a distribution over here. And it's saying I'm super, super confident in my decisions despite the fact that I'm wrong. So that's kind of a intuitive argument for a hinged loss. And this is in two-dimensional space, but in high-dimensional space, everything gets even more crazy, and this becomes even more important. So, any questions here? Yeah.
Sorry, I missed that one. Under what situation does that occur?
Oh, so yeah, I can give an example. So normally, when you calculate, let's say we're calculating our softmax, right? Or I can do sigmoid. So the sigmoid basically on the sigmoid x will always look like this. But what your neural network classifier can do is it can make x really large, negative or positive. So it will make the scale of x really, really huge, and as a result, the x over here will be like 5,000, and 10,000, 100,000, or something like that, and it will become basically a step function. Good question. Any others? Yeah.
So you said that support vector machine is one of the concepts of traditional machine learning that is still not obsolete. So can you give some practical examples where it's still very relevant, especially compared to neural networks?
Oh, can I give any examples where support vector machines are really relevant compared to neural networks? That's a good question. If I have a really, really small data problem where I want to apply a classifier to it, I will not apply a support vector machine, but I will potentially apply gradient boosted decision trees or something like this. So there are other machine learning algorithms that you might want to use other than neural networks. Honestly, I haven't come across a problem recently where support vector machines do better than either of those two options. So other people might disagree with that. You might have counterexamples, but me personally, that's my experience. Yeah. Any other questions? Yeah, so XGBoost is a good gradient boosted decision tree library that is used to win like all the Kaggle competitions. So if you want to do like small data type things, then that's often a good choice. Okay. So there's another thing called cost-augmented hinge loss. This was mentioned in the reading briefly, but I'd like to give a more intuitive example. So sometimes some decisions are worse than others. The typical example of this in your generic machine learning class is like overdiagnosing people for cancer or underdiagnosing people for cancer, and which one is a bigger problem. To give an NLP-related example, you have a verb versus VBP mistake. So these things are very similar, in their usage patterns and stuff like this. But let's say you had a verb to a noun mistake. This might mess up your whole sentence structure or something like this. Maybe over-recognizing an entity in a named entity recognition system is not a problem, but under-recognizing would be a big problem if you wanted to detect like all the information you wanted high recall. So there's lots of examples like this, and what the cost-augmented hinge loss does is it defines a cost for each incorrect decision and sets a margin equal to this. So basically we have our cost, y hat, y, where y is the correct value, and y hat is the thing that we predicted. And this cost can be higher or lower depending on the difference between them. So one example of this would be the cost between VB and VBP might be 0.5, and the cost between VB and N might be 2. So then your margin for a mistake between VB and N would be 4 times larger than your cost between VB and VBP. So how do we do this over sequences? There's a really nice trick that allows you to do this over sequences. Sorry, I'll get there in a second. So first, how can we define costs over sequences? So the costs over these are relatively clear, I guess. It's, if you have a multi-class classification problem, you just have a different cost for each type of mistake. You have like a matrix of costs over each type of confusion, and you define this for each one, and then you can apply that. But over sequences, what do we do? The first one is 0-1 loss. So you have a loss of 1 if the sentences differ, and 0 otherwise. So this is kind of interesting. What does this look like? This looks like our regular hinge loss, right? We have a margin of 1 for every mistake, or every possible mistake we make, and we have a margin of 0 if we don't make a mistake, so then we don't have any problem. So that's what that looks like. But however, if you think about sequences, getting everything wrong is probably worse than getting one thing wrong, right? So Hamming loss, what that says is you get 1 for every different element in the output. So every element in the output that's different, you get a cost of 1. This assumes that the links are identical, so you can just read it off, and that's what this looks like. So you have a sum over the differences between each of the elements. Oh, sorry, the delta function here, I don't know if I explained this. This is the Kronecker delta function. It's basically 1 if the condition is true, and 0 otherwise. You can think of a ton of other losses as well. So you can think of edit distance, 1 minus blue score if you're doing machine translation. If you're doing parsing and F1 is the F1 score is the thing you care about, it's 1 minus F1 score. Anything where higher is worse. So if you have an evaluation metric where higher is better, you just do 1 minus that evaluation metric, and you have a good loss, a good cost. So what structured hinge loss looks like is basically it's a hinge loss over sequences with the largest margin violation. So what you do is instead of searching for the sequence that has the highest score overall, you search for the sequence that has the highest score plus cost. So essentially what you're trying to do, and this is your cost-augmented hinge loss function. So essentially what you're trying to do is you're trying to search for things that have a high score and are really bad. So that's a good thing that you want to penalize, right? Because you don't want bad things to have a high score. So you combine these two things together. Maybe if there's something with a little tiny mistake, you don't really care if its score is pretty close to the score of your best scoring output. So then one question becomes, how do we find the argmax above? And the solution is in some cases where the loss can be calculated easily, we can consider this loss at search time. So here's an example, cost-augmented decoding for the Hamming loss. So Hamming loss is decomposable over each word. So what we do is we add a score equals cost to each incorrect choice during search. So like let's say we have a choice here, I, and we want to predict its part of speech tag. We have all of these scores. So what we do is we take all but the correct part of speech tag, and we add 1 to it. Because that would be the cost of making a mistake on that on this particular part of speech tag. So now we get a noun. with a score of 1.5. And despite the fact that PRP had a score of 1.3, now noun has a score of 1.5, so we picked this instead of the thing that originally would have been the higher score. So now we make a mistake, we get noun, and now we're in trouble because we've made a mistake at the very beginning of the sentence, and now we get a whole bunch of other things incorrect too. So I like to call this like evil teacher forcing, because it's an evil teacher that tries to make you make mistakes on every quiz question, so you get more and more confused until you get to the end of the sequence. But this hasn't caught on, unfortunately. Nobody actually calls this in papers. So, yeah. But I think the nice thing about this is it's a really, MLE is really susceptible to exposure bias, right? Because you're assuming that every single prediction you made previously was correct. So in this case, now you have something that's super, super robust to exposure bias, because in order to get the correct context, you need to overcome this massive bias against getting the correct answer, because you're giving a bonus to everything but the correct answer. Okay. So are there any questions about this? Okay. So in addition to all of the search-based algorithms that I explained here, so the search-based algorithms that I explained here, I feel like these and like the reinforcement learning things I'm going to be talking about in next class are kind of like the quote-unquote right way to do things. They have good theoretical interpretations. I can explain them very intuitively, and they're closely connected with your search algorithm and stuff like this. The big disadvantage of these types of methods is that they tend to be slow, because you have to do search during training. And if you're training over an absolutely massive data set, then at the very least you'll have to train with MLE first, and then gradually transition into something like this. However, there are simpler methods to remedy exposure bias. So that's what I just said. So there are simpler methods to remedy exposure bias. One of them is sampling mistakes during training. So this was what was called Dagger in the in the reading. And what it does is it basically samples outputs randomly with respect to wrong decisions and feeds them in. So basically what you do is you calculate the loss of the correct answer, and you randomly, but when you calculate the thing that you feed into your neural network, you instead randomly sample a mistake. So Dagger, the paper here is very nice. It has these theoretical interpretations of this. It's also from CMU, so go CMU. But there's also another paper after that called Scheduled Sampling, which kind of applied this to neural network-based models. And the exposition there is simpler. Basically, it's saying, we tried this and it works. So it doesn't have the theoretical stuff, but it does have one very nice thing relevant to neural networks, which is they do pre-training, and they start with no mistakes in the output, and then they gradually introduce more mistakes as you go in. So this is like what I talked about with the MLE pre-training, and they also discuss different schedules with which you can gradually introduce more mistakes. So this is good in some cases. One case where this would be a good idea, I think, is something like part-of-speech tagging. And the reason why it's a good idea in part-of-speech tagging is because in part-of-speech tagging, you have one tag per word, and you can sample mistaken tags and try to still recover in that case. However, things it's not quite as good at are things like machine translation. And the reason why machine translation is not, this is not the best idea to apply it there, is, or text generation in general, is if you have any sort of ambiguity in the output that you're expecting, like let's say we had the Japanese sentence, corresponding to the dog barked. In Japanese, there's no marking of plural in this sentence, so another option would be dogs barked. So we have these two options, right? And so what we would do is we really have no idea, so we would kind of randomly sample one of the first ones. This one is the reference. So we randomly sampled dogs. And now we input dogs, and the next thing we need to predict is dog. So we input dogs, and then we output dog. And that's not a good thing, because now we're basically optimizing the probability of dog barked, right? So this is a super simple example, and of course there's many more complicated examples, like when you could have two alternative clause reorderings or something like this. So it's a pretty good idea when there's like only one correct answer, or where you can assume the outputs are synchronized like we can for part of speech tagging. It's less of a good idea for things where you might do like text generation or something. So because of this, there's also a concept of something called the dynamic oracle. And basically what the dynamic oracle is something that tells you which thing you should be predicting next, given the things that you've already predicted. So in this case, what a dynamic oracle might look like is figuring out that dogs and dog kind of look similar, and saying if dogs and dog kind of look similar, maybe I shouldn't be predicting dog next, but instead I should be predicting barked next. This is kind of vague in the case of machine translation, so it's not actually used super widely in MT or anything like this, although there's a paper or two on this. But for things like parsing or other sorts of structured prediction tasks, it's actually easy to deterministically define this quote-unquote dynamic oracle that would give you the best prediction that would maximize the accuracy for the rest of the predictions. So that's something that you can take a look at if you're interested. Another simple solution to exposure bias, or to making repeated mistakes based on the things that you fed in, is to drop out inputs. And the basic idea is simply, you want to simply not input the previous decision sometimes during training. What we would normally have is something like this, and basically all we do is we drop this out and we input a zero vector instead, some fixed percentage of the time, like 0.3% of the time or 0.5% of the time. And what this does is it basically makes the model able to use context, but also robust in cases where the context is not very informative. The difficulty with this is the amount of dropout you apply here is a hyperparameter. And of course, the weaker this hyperparameter is, the more it will rely on context. The stronger the hyperparameter is, the less it will rely on context. So you need to adjust that carefully in order to get this correct, basically. But this is it's super easy to implement, obviously, so yeah.
So when we are inputting the zero vector, will the model treat it as a specific clue, or would it like take the zero input as some random information and try to predict based on that?
Would it take the zero input as some kind of information and try to predict on that? I think that's a good point. It would take the zero input as maybe lack of information and use that lack of information to say, I don't know what the context is, so I'll just ignore the context. However, at test time, it would be silly to not feed in the previous information unless we were really uncertain of it or something like that. But it would be silly to not feed in the previous information. So if the model is smart enough that it can say, if I see a zero vector, ignore it, otherwise use it 100% of the time, then it will do that, basically. Actually, we have I don't think I have it in the slides. Yeah, I don't have it in the slides, but I think that is indeed what happens. And because of that, the next thing is actually maybe the better thing to do here. So the next thing, this is corrupting training data. And basically the idea is the name is reward augmented maximum likelihood. And the basic idea is that we randomly sample incorrect training data, but then train with maximum likelihood. So if we have an input like this, where this is the input and this is the output, we have a training example. What we do is we randomly sample perturbations to this before even training the model whatsoever. And then we do maximum likelihood estimation with respect to these perturbed inputs. So how do we do this? We're not sampling according to the model, so what are we sampling according to? And basically the idea is you have a sampling probability that is proportional to the goodness of the output. And the actual way we do this is we have something so we have this between the perturbed output y, I'll call this y tilde. The perturbed output y tilde and the actual output y. And the probability is basically inversely correlated with the cost. So if we have the perfect output, that has a cost of 0, so basically it's no error whatsoever, this will be 0. Which means this e to the 0 is 1, right? Anything that has a cost of greater than 0 will be smaller than 1. And because of this, we are most likely to sample the thing with the cost of 0. We're less likely to sample anything that has a cost of greater than 0. And we also have a parameter, or let me call it alpha, or we can call it tau, the temperature, which controls the peakiness of this distribution. So this is something called the exponentiated payoff distribution, and basically it means that if we have this tau be very small, small, the distribution will be very peaky, and most of the time we will sample correct things. If we make the tau a little bit larger, we will have the distribution be not so peaky, and we might be sampling lots of mistakes and training towards them. This can be shown to approximately minimize the risk, which I'll talk about in the next class. But basically, it's a simple method here. Yeah.
So when you're training, how is this different to the dagger method? Because either way, you're getting a wrong tag.
Yeah. So that's a good question. How is this different from the dagger method? Either way, you're getting the wrong tag. The difference here is basically that you're sampling according to the goodness as opposed to what the model thinks. Also, the mistakes are going to be a lot less consistent here. So this method's a little bit counterintuitive. Like I didn't fully understand it when I saw it myself, but basically the idea is you're much more likely to sample things that have lower cost, and that is going to be good because basically the distribution of things you're going to be seeing is likely to be correct. That doesn't hold for dagger, right? Or that doesn't hold for scheduled sampling. So because of that, I think that's the main intuition difference there. The good thing about this, compared to just dropping out the words, is it can't just learn to ignore a zero vector, right? It has to essentially distinguish between when the sampled output is incorrect or not. So, yeah. So I guess that's all I have for today. I know this was relatively kind of more mathematically heavy than some of the things that I've done before. I'm happy to take any questions that people had, or yeah.
So how do these three solutions like compare? Which one you choose?
Oh, good question. So how do they compare empirically? This is a very surprisingly effective method, basically. And I think part of the reason why is dropping out the inputs, the model can learn to ignore when you have a zero vector. It has a hyperparameter that it's very sensitive to. This is also sensitive to the tau hyperparameter as well, so it's not sensitive. But empirically, this is quite effective, I think. Another thing is you're only sampling local perturbations, so you're also very unlikely to have like dog's dog barked. It's going to be more like pancake dog barked, or like some other like completely unrelated thing. So maybe it's a little bit easier to abstract away from that noise. But another thing is this is ridiculously easy to implement. It's just as easy as word dropout, and you just corrupt the data before you feed it into your models. So, yeah.
Not that it's designed to reduce exposure bias, but could beam search help if you're kind of like keeping beams with not the tag that you predicted, but maybe some other tags?
Yes. So could beam search help? Beam search itself cannot help if you don't train using beam search. Within this structured hinge loss formulation, you would be doing beam search to search for the highest scoring thing. So in this case, you are doing you would be doing beam search to do this argmax in the first place. So if you're doing beam search at test time also, then this is a really good method for that. There's also something else a bit more complicated. There's something else a bit more complicated that I didn't cover here, but it's a nice method. So, and since you asked, I'll talk about it. It's this paper called Sequence Learning as Beam Search Optimization. And basically, the idea is pretty well described by this figure here. And they have this kind of nice, interesting formula where the yellow one is the correct answer. And so what you do is you do beam search step by step, and you search until the correct answer falls off the beam, basically, until the correct answer is no longer on the beam. And you detect when this happens, and then you say, okay, it fell off the beam here. Here is the hypothesis that caused it to fall off the beam. So what I will do is I will replace the correct hypothesis back on the beam. I'll boost its score till it comes back on the beam, and then I'll continue search to the end of the sentence. And now we have basically a search graph up until the place where we failed, and then we have the competing hypothesis. We search again until the place where we failed, we have the competing hypothesis. So this is a more direct way of incorporating it, like actually in beam search. But as you might imagine, just looking at this graph, this is not super easy to implement, especially efficiently. So I think it's a beautiful method, but it's less widely used simply because it's harder to implement or less efficient. Any other questions? Yeah.
Would it be useful for beam search in general for the probabilities over the vocabulary to be calibrated?
Would it be better for beam search to have calibrated probabilities? I think the answer is yes. That's a good question, and I can't answer like definitively yes, but I can answer I think the answer is yes.
And is there any effort in trying to do that?
And is there any effort in trying to do that? I can't. There's efforts in diverse beam search, but I don't think there's effort, like as far as I know, I don't know if there are efforts in training models to allow for the better calibration during beam search. So hey, project idea. Um, uh, since we're talking about it, or no, actually, maybe I'll relegate it to next Thursday because we're talking about search then. So what I was going to say was I was going to start talking about like diverse beam search and also the mistakes that beam search tends to make, but I'll try to do that next time. So, yeah. Any other things? Yeah.
So the nature of hinge loss makes the gradient kind of agnostic to the actual magnitude of the loss. Do you think that is a problem?
The nature of hinge loss makes the magnitude of the gradient agnostic to the size of the loss. Is that a problem? Maybe, yeah. That seems like a reasonable that seems like a reasonable concern. There's also other varieties of hinge loss. I'm blanking on the name. There's like softmax margin, I guess. There's something called softmax margin, which is a little bit like this. That it might handle that to some extent, but that's a good question. Any other questions? Yeah.
So, in case we try to use like the beam search kind of stuff over here, that we don't have like the exact probability values, but rather like score values.
Yeah.
So in that case, when we have the issue that at each and every iteration, we might have scores which have different kind of range because of maybe the confidence or something like that. And as a result, in probability, I still might be able to say that it is getting conditioned and we might have a better value. But in score, if I just not add it, like, and I have like n top values, will it still be like head-to-head comparison?
So that's a really good question as well. So the question is, when you're doing beam search, it's really important to compare across different predictions. So like if you're predicting one word and then the next word, then the next word, then the next word. So in that case, if you're not using probability values, would that cause your search to kind of go haywire and not find good outputs? And interestingly, there's a paper by Kardik here, Kardik Goyal. So this is, they basically compared globally normalized and locally normalized models. And they have, there's also a model called a self-normalized model, where the self-normalized model, basically what it tries to do is it doesn't actually calculate the partition function during, it doesn't actually calculate the partition function, but it tries to learn probabilities so the partition function is 0. So, well, it calculates the partition function and tries to match the probability so the partition function is 0. And what this means is at test time, you don't need to do normalization. So what you can do is you can turn, in that case, you can turn normalization off and you still get reasonably good scores. However, if you take a locally normalized model and don't take the softmax, you just take the logits and calculate the max score according to the logits, you get really, really bad accuracy. And basically, it shows the locally normalized model is really heavily, depending on that normalized probability. But a model that's trained so that it self-normalizes doesn't really depend on it that much. So my answer is I don't know the answer with respect to like hinge loss or something like that, but I expect that since it was incorporating the search algorithm in training, it will probably have already accounted for that, and it won't be a problem. So, but I think this is an interesting paper if you like this, and Kardik is here, so you can go talk to him. Yeah, any others? Yeah.
So I have a question regarding the first objective, loss objective that you introduced before the cost-augmented term. Was just the max score over all the y-dashes minus the max score of the golden y.
Yep.
So that would teach the model to tell the gold y apart from any other y, right?
Mhm.
but that, how would the model learn to actually rank the non-gold wise among them?
So you're talking about this one here, right?
Yeah.
So how would it learn to rank the non-gold wise? So that's a good question. There's two answers. One answer is implicitly. It would learn to rank the non-gold wise because it's easier to like, I guess more highly confusable things are, sorry, less highly confusable things are going to be learned very early in the training process. So things that are just completely implausible are very quickly going to be filtered out. They're going to be given really low scores. More highly, you know, confusable things are going to take longer. They're going to be in the border near the end of training. So implicitly, it will learn to do something like that. However, if you do have a ranking, like according to a cost, you can also explicitly optimize that ranking as well. There are ranking-based loss functions, which I didn't cover here, but that's something you can do. The question is, what is your ranking though? Like, is your ranking, you know, the correct one is better than all the others? Then if that's the case, then this is a perfectly fine loss function. So, yeah. Any other questions? Okay, if not, I'll finish up. So very good questions, thanks a lot.